There is a specific kind of quiet that belongs to late hours, not silence exactly, more like the absence of the day's insistence, the way sound doesn't disappear so much as it stops trying. You know this quiet. You're in it right now, or something close to it. And the fact that you're here at all, at this hour, with this particular kind of attention that only arrives when the rest of you has stood down, that matters, though not in a way that needs explaining. Sleepy Science Channel has been sitting in this same hour with people for a while now, and there's something that still feels strange about it, in a good way, like a conversation that keeps getting continued even though no one planned it. The people who keep it going, who decided at some point that this was worth a few dollars a month, there's a gratitude for that which doesn't fit neatly into a sentence, so it just lives here, between the words, the way most true things do. Ow. Look up. Not actually up. You're horizontal probably, or close enough. But look up in the way you do when you're thinking about the sky without seeing it, when the ceiling becomes temporarily transparent in your mind, and you find yourself registering the fact of it all, the distance, the scale, the sheer amount of nothing you've been told is up there, the gaps between stars, the dark parts, the places where the eye goes and finds no purchase and slides off the edge of its own attention. You've been told those places are empty. You were told this early, and it was told to you as though it were the obvious part, the uninteresting part, the backdrop against which the real things, the stars, the planets, the burning and the spinning, take place. The dark is the stage, the light is the show. That's the version most people carry. And it's not wrong exactly, it's just. And this is the part that takes a moment to land. It's wrong about the stage. The thread this chapter follows is a thin one. It does not branch. It goes from one end to the other, and the thing it pulls through is simply this, that the space between stars, the gap, the interval, the dark, it is not empty. It has never been empty. And the word empty is not just imprecise in a technical footnote level way. It is imprecise in the way that changes what you're looking at when you look at it. Once this settles, the sky doesn't look the same. Not more dramatic, not more frightening, at least not immediately. Just fuller, denser, like a room you thought was one size and then walked all the way into. But we're not there yet. We're still outside. We're still at the distance where the gaps look dark. Stand for a moment at the edge of what the eye can do. You look at the sky on a clear night, truly clear, the kind of clear that requires being somewhere inconveniently far from electricity, and you see, depending on your eyesight and your patience, somewhere between 2,000 and 5,000 individual stars. You see the Milky Way as a smear, a suggestion, a river that your eye insists is made of light, even though most of what you're seeing is the combined glow of things too small to resolve individually. And between all of it, between the stars you can name and the ones you can't, and the galaxy smear and the faint wobble of what might be a planet, between all of that, there is the dark. And the dark is enormous, far larger by volume than all the lit things combined. If you could calculate the ratio, and people have, the fraction of space occupied by stars and planets and moons and all the glowing and reflecting things we tend to point at would be almost too small to express in ordinary numbers. The rest is the interval, the gap, the between. This is what we're going to follow, the between. There is an experiment, not a thought experiment, an actual one, conducted with instruments far more patient than eyes, where you point a radio telescope at a region of sky that contains, as far as optical observation is concerned, nothing. No star in the foreground, no galaxy in the background, no identifiable source. You point it at the dark and you listen, and the dark talks back. Not metaphorically, not in the poetic sense where we say that nature speaks to us and means something vague and inspirational. Literally, the space between stars emits radiation at specific predictable frequencies. The most well-known of these is at a wavelength of 21 centimeters, the hyperfine transition of neutral hydrogen, which is exactly as technical sounding as it needs to be and exactly as simple as it actually is. A hydrogen atom sitting alone in the cold between stars occasionally releases a tiny amount of energy, a photon, a signal. It does this without prompting, without reason, in the way that quantum systems sometimes just go from one state to another because the probability of it is not zero. That signal travels. It travels through the medium it came from, through the rest of the gas and dust and charged particles and magnetic fields that fill the interval, and eventually, if something is pointing in the right direction and listening, it arrives. The dark is broadcasting. It has been broadcasting since there were hydrogen atoms, which is to say since approximately the beginning. We just needed to build something that could hear it. The first time this was measured, the first time someone held up an instrument and the instrument said, yes, something is here, in the gap, in the nothing. Here is a signal from a place you thought was silent. It did not make headlines the way certain discoveries do. It arrived, as most true things do, quietly. A confirmation of something that has been predicted, a prediction made by people who were already fairly certain the medium existed, but needed the number, needed the signal, needed the data that would let the idea harden into fact. The measurement happened. The fact hardened. And then, the way science works, everyone moved on to the next measurement. But the sky had changed. The interval had changed. The dark gaps between stars and the ones you look at and feel nothing looking back. They were no longer gaps in the way a missing floorboard is a gap or a space between furniture is a gap. They were a medium. They had texture. They had behavior. They were full of something that was doing things slowly, on timescales that make the word slow feel like a gesture toward an idea rather than a description of it. The word for this, for the gas and dust and plasma and magnetic fields and cosmic rays that fill the space between stars, is the interstellar medium. It enters here once. It will be felt for the rest of this audio. Now hold the thread. The dark gaps in the sky are filled, not with a lot. The interstellar medium is sparse enough that any vacuum we could engineer on Earth would be considered packed with matter by comparison. But sparse is not absent. Thin is not nothing. The scale of interstellar space is large enough that even a near vacuum becomes, across light years of distance, a substantial thing with real weight and real influence. Astronomers who work with it don't think of it as the backdrop. They think of it the way you'd think of a fluid, a medium that carries waves, that has pressure, that pushes back when pushed, that responds to energy and stores it and releases it on its own schedule. The thread runs through all of this. Follow it. Look at the darkest gaps in the night sky and you'll see nothingness. That's not an error of perception. The gaps are genuinely dark. The light doesn't reach. But sensors reveal a different account, one that is not dramatic so much as it is patient. Hidden within that void are filaments of a cosmic structure, threads of gas and magnetism and charged particles and cold dense clouds, and this structure has a say in everything, in which direction stars can form, where matter accumulates, how long a cloud of hydrogen drifts before it collapses into something burning. It is a hidden map, not drawn by anyone, not pointing anywhere in particular, but real and consequential in the way that invisible things are sometimes more consequential than visible ones. We move through it. Everything in the galaxy moves through it. We are not observing it from outside. We're caught in it. We have always been caught in it. We just didn't know the stage had walls. The thread ends here for now. Not because it ran out. It goes much further, and the next chapter will find it and follow it somewhere else. But because this is where the idea should be allowed to sit for a moment, before it's handed another task. The dark is not empty. The dark has texture. The dark is doing something on its own, without our attention, in the interval between the things we named first. That's the only thing this chapter was carrying. It has put it down. Something has already happened by the time this chapter opens. A source emitted. The emission travelled. The distance between source and destination was, by any human measure, absurd. Not large the way a continent is large, not large the way an ocean crossing is large, but large in the way that makes those comparisons feel like a category error. The way comparing a match flame to a star is technically valid and practically useless. The light left, the light travelled, and somewhere in the travelling the record of its journey got written into it, not as memory because photons do not remember, but as change, as alteration, as a signal that arrives slightly different from how it departed, and that difference, that small gap between the sent version and the received version, is what this chapter is made of. The photon arrived, changed, or it didn't arrive at all. Both cases tell you something. Astronomers have a word for light that has been altered by passage through the interstellar medium. They call it reddened. Not red, reddened. The distinction is subtle, but it sits right at the centre of what the interstellar medium actually does to the light trying to pass through it. Dust grains, and the medium is full of them. Not thickly, not in any way you'd see if you were floating in it, but persistently. Scatter and absorb shorter wavelengths of light more efficiently than longer ones. Blue light, with its shorter wavelength, gets deflected or swallowed. Red light, with its longer wavelength, passes through more easily. The star on the far side of a dust cloud doesn't look red. It looks redder than it should. It looks like it has been dragged slightly toward one end of the spectrum by everything it passed through. This is called interstellar extinction, an interstellar reddening. The medium leaves its fingerprint on the light. That fingerprint is data. The idea settles in layers here, the way sediment does, not announced, not argued, just deposited quietly and allowed to accumulate. First layer, the interstellar medium is not transparent. It appears transparent from the outside because the gaps between stars look dark rather than foggy. But transparent and dark are not the same condition. The medium does not glow mostly. It absorbs and scatters rather than blocks in the obvious way. A thing can be optically thin, meaning most light passes through and still alter every photon that crosses it. Second layer, the alteration is wavelength dependent. Different kinds of light interact with the medium differently. X-rays pass through relatively easily. optical light, the kind eyes respond to, gets reddened. Infrared passes through dust better than visible light does, which is why infrared telescopes can see into and through dusty regions that optical telescopes cannot. Radio waves pass through almost entirely unaffected, which is why that 21 centimeter hydrogen signal from the previous chapter travels so cleanly across the galaxy. Third layer, every wavelength of light then arrives carrying a report on what it crossed. The report is not written in language. It is written in the shape of the spectrum, in which frequencies are missing, which are attenuated, which are shifted, which are scattered away, and which are not. A spectrograph pointed at a distant star is not just measuring the star. It is measuring everything between the star and the telescope. The medium writes itself onto the light. There is a photon, and this is not metaphor, this is the actual physics. There is a photon that left a star some thousands of light years away, travelled through molecular clouds and diffuse gas and through regions where the magnetic field bent its path by a fraction too small to name, and arrived at Earth carrying in its spectrum the record of every dust grain it passed near enough to interact with. It arrived changed. A spectrograph caught it. The spectrum showed absorption lines that did not belong to the star, lines that belonged to the medium, to the gas it crossed, to the molecules present in the cold, dense clouds it threaded through. We read those lines, we identified the molecules, we found things in those absorption lines, things like polycyclic aromatic hydrocarbons, complex carbon molecules, molecules that have no business existing in space by any naive accounting of chemistry, and yet there they are, in the spectrum, in the fingerprint, in the record the medium wrote onto the light. The photon carried mail it didn't know it was carrying. Now the other case, the photon that did not arrive, a source at a known distance, a known brightness, a known spectral type. You point your telescope at it, and the flux is lower than predicted. Not a little lower. Lower in a way that cannot be explained by the star being different from what you calculated. The missing light went somewhere. It was absorbed. It was scattered out of your line of sight. The medium between you and the source took some of it. This is called extinction magnitude. Astronomers measure it. They correct for it. When they want to know the true brightness of a distant star, they measure how much the medium has dimmed it, and they add that back in, mathematically, so the final number reflects the star and not the journey. But to do that, you have to model the medium. You have to know what the medium is, how dense it is along that particular line of sight, what kind of dust is in it, what its column density is. The missing light forces you to account for the thing that took it. The absence of the photon makes the medium visible in the only way a near-invisible thing can be made visible, by what it takes away. There is a duration embedded in all of this that is easy to slide past without noticing. The light that carries the record of its crossing took thousands of years to cross. The medium it passed through was not the same medium at the end of the journey as it was at the beginning. Clouds move, densities shift, stars form inside the clouds, and their radiation ionizes the surrounding gas, and the gas that was there when the photon entered the medium is not the same gas the photon was still travelling through 10,000 years later. The photon crossed a thing that was changing as it crossed it. The record it carries is not a snapshot. It is a time-averaged blur a composite of every version of the medium it encountered over the full length of the journey. The fingerprint is not of a single moment. It is of a duration. It is in a sense a recording of time more than of space. What this means, and this is the layer that settles last, the one that takes a moment to find its place, is that the medium is not a static object to be measured once and filed. It is a process, a continuous slow event. The dust grains that reddened a photon 10,000 years ago are not the same grains that will redden a photon leaving the same star tonight, because the grains are themselves part of a cycle. They form in stellar winds, they drift through the medium, they get processed by radiation, they accrete icy mantles in cold clouds, they get shattered by shock waves from supernovae, they get incorporated into new stars and planetary systems, and eventually into the solid objects that form around those stars. The grain that reddened the light is not waiting patiently to be described. It is already somewhere else, doing something else, having been altered by everything it touched since it last touched the light. The record the photon carries is of a thing that no longer exists in quite the form it was recorded. This is not a problem for the science. The science accounts for it, models it, works with it. But it is worth sitting with for a moment, that the information encoded in the light is information about a version of the medium that is already past, already dissolved into the next version of itself, already somewhere further along in its own long rearrangement. The photon carried a message from something that, by the time the message arrived, had already moved on. You are inside a cloud, not a weather cloud, not the kind with moisture and turbulence and the grey light of an overcast afternoon. A molecular cloud, one of the dense cold regions of the interstellar medium where gas has gathered thickly enough by interstellar standards to shield itself from the radiation that would otherwise break its molecules apart. You're inside it, which means almost nothing surrounds you, except that the almost nothing is everywhere, and there is an enormous amount of it, and you are, in the most technical sense possible, completely surrounded by a substance that contains roughly 100 to 1,000,000 molecules per cubic centimetre. For comparison, the air you are breathing right now contains approximately 27 million billion molecules per cubic centimetre. The cloud is not dense, and yet the temperature here, and temperature is already a complicated word in this context, as will become apparent, is somewhere between 10 and 30 Kelvin. 10 Kelvin is negative 263 degrees Celsius. It is, by the standards of everything you have ever touched or stood near or breathed, incomprehensibly cold. Colder than anything that exists naturally on Earth's surface. Colder than the surface of Pluto. Close, within a few degrees, to the coldest temperature that physics permits. But here is where the uncertainty begins, and the narrator is going to stay in it rather than resolve it too quickly, because the uncertainty is the interesting part. Temperature, in the way we usually mean it, is a measure of the average kinetic energy of particles. How fast they are moving, how hard they are hitting each other, how much energy is stored in their motion. In a gas at room temperature, particles are colliding constantly, exchanging energy, reaching what's called thermal equilibrium, a state where the energy is distributed evenly enough that a single number, the temperature, can describe the whole system meaningfully. In the molecular cloud, the particles are so spread out that they barely collide at all. the sound of this place, if sound could propagate through it. And it almost cannot, because sound requires collisions, requires the mechanical transmission of pressure from one particle to the next. And the particles here are so rarely near each other that a pressure wave would barely move before losing coherence. The sound of this place would be the sound of nothing, which is different from silence, the way a vacuum is different from a quiet room. Silence is the absence of sound in a place where sound is possible. This is a place where sound is almost not possible. The molecules drift. They vibrate internally. Each bond in each molecule has its own resonant frequencies, its own way of absorbing and releasing energy, its own hum that nothing nearby is close enough to hear. The cloud has temperature in the sense that the molecules have kinetic energy, are moving, are not absolutely still, but it has temperature the way a single instrument playing in an empty concert hall has sound. Technically present, physically real, but missing everything that makes the word feel like it means what it usually means. There is a measurement. It is called the excitation temperature. It describes not how fast the molecules are moving, but how they are distributed across their internal energy states, which rotational or vibrational levels are occupied, and in what proportions. In thermal equilibrium, these two numbers, kinetic temperature and excitation temperature, are the same. The motion of the molecules and the internal states of the molecules are in conversation with each other, exchanging energy constantly, staying matched. In the cold molecular cloud, they are not the same. The gas is so thin that collisions, the mechanism by which kinetic and excitation temperatures equilibrate, happen rarely. A molecule can be in an excited internal state for a long time before it encounters another molecule and has the chance to transfer that energy. Meanwhile, photons from distant sources can pump energy into specific internal transitions without raising the overall kinetic temperature of the gas. The excitation temperature and the kinetic temperature drift apart. The cloud has, in a sense, two temperatures. They are measuring different things. Neither one is wrong. Both of them are real. And the number, the 10 to 30 Kelvin that was given at the start, is the kinetic temperature, which is the one that feels most like temperature in the familiar sense. But it is not the only number that describes what is happening in here. The cold matters because of what it permits. At these temperatures, molecules can form and survive. Not easily. Chemistry in the interstellar medium happens slowly, on timescales measured in millions of years. But the cold shields the molecules from the radiation that would break them apart. The outer edges of the molecular cloud absorb the ultraviolet photons that would photodissociate the molecules in the interior. The interior stays cold enough and shielded enough for chemistry to proceed, and the chemistry is not simple. Astronomers have detected in molecular clouds over 200 distinct molecular species. Some of them are small: hydrogen, carbon monoxide, water, ammonia. Some of them are large and complicated: long carbon chains, ring structures, molecules with enough atoms that their detection came as a surprise to people who had assumed that complex organic chemistry required something warmer, something more energetic, something more like a planet. The cold is the condition. The cold is what allows the complexity. Without the temperature that registers as nearly absolute zero on the thermometer, the molecules don't last long enough to find each other, to react, to build the structures that get incorporated into the clouds that collapse into the stars that produce the planets where temperature, ordinary, familiar, life-sustaining temperature, finally becomes the right word for what is happening. The pulse, here. The cloud is not static. It breathes in a sense that is only slightly metaphorical. Turbulence moves through it, not thermal turbulence, which requires collisions, but magneto-hydrodynamic turbulence, waves in the coupled system of the gas and the magnetic field threading through it. These waves compress regions of the cloud and rarefy others. The compressed regions get denser. If they get dense enough, they can begin to collapse under their own gravity. This is how stars start, inside the cold, and then the collapse releases gravitational energy, which heats the collapsing material, which raises the temperature, which eventually reaches the point where nuclear fusion ignites. The star turns on, its radiation heats and ionizes the surrounding gas. The molecular cloud, or what remains of it near the new star, warms. The chemistry that the cold protected gets destroyed by the heat the star produces. The cloud made the star. The star undid the cloud. Then the pulse contracts. New gas drifts in, slowly, over millions of years. The density builds again. The shielding rebuilds. The cold returns. It is possible that this is not fully understood. The narrator will say this plainly. The temperature structure of molecular clouds, the role of turbulence in triggering collapse versus preventing it, the precise pathways by which complex molecules form on the surfaces of dust grains at 10 Kelvin. These are active research areas. The broad picture is solid. The details are not all settled. The 10 Kelvin number is real. The chemistry is real. The sequence from cold cloud to star is real. But the way the temperatures don't quite mean what they seem to mean, the way excitation and kinetic decouple in the thin cold gas, the way a cloud can have a temperature that describes its motion and a different temperature that describes its internal quantum states, and both numbers are accurate and neither one fully captures what it is like to be in there. That part is still being worked out. Not wrong, just not finished. Something in the cold resists being described all the way to the end. Stand at the edge of what is about to change. A dense core inside a molecular cloud, a region perhaps 1/10 of a light year across, containing somewhere between 1 and a few solar masses of cold gas, has reached a threshold. Its internal pressure, the thermal pressure, and the turbulent pressure, and the magnetic pressure that have been holding it up against its own gravity, is no longer enough. Gravity has won, or is about to win, in the way that outcomes in physics announce themselves before they fully arrive. A slight imbalance, a small net inward acceleration, a beginning that looks almost indistinguishable from the equilibrium it is ending. This is the moment before a star. We are watching from the outside of this event, but not from far outside, close enough to see the scale of what surrounds the collapsing core, the medium it sits in, the larger cloud it belongs to, the arm of the galaxy the cloud is embedded in, and close enough to understand that the core is not an isolated object falling inward in empty space. It is a node in a structure, and the structure is everything. Pull back, just slightly, to the scale of the molecular cloud itself. A large molecular cloud, the kind called a giant molecular cloud, can stretch across hundreds of light years and contain millions of solar masses of material. The Orion molecular cloud, which is near enough that it has been studied in extraordinary detail, spans several hundred light years and contains enough material to form 100,000 stars. It is not uniform. It has dense filaments running through it, and dense cores embedded in those filaments, and in some of those cores stars are forming right now, at this moment, in the same sense that any process occurring across thousands of years can be said to be happening right now. The cloud is not a blob. It has structure. It has hierarchy. There are large features made of smaller features still, and at each scale the physics is slightly different. Different forces dominating, different time scales operating, different processes competing for control of what happens next. This hierarchy did not assemble itself by accident. The structure of a molecular cloud is shaped by the interstellar medium it condensed from, by the turbulence that the medium carries, by the magnetic field that threads through the medium and into the cloud and through the filaments and into the cores, organizing and supporting and sometimes channeling the flow of material at every scale simultaneously. Pull back further, to the scale of the galaxy. The molecular clouds are not distributed randomly across the Milky Way. They concentrate in the spiral arms, which are regions where the density wave of the galaxy's gravitational structure has compressed the interstellar medium, triggering the formation of the clouds in the first place. The spiral arms are not made of specific stars. The stars move through them, drift out the other side, spend only a fraction of their lives inside the arm that formed them. The arms are made of the medium, of the compressed and structured interstellar gas that the density wave drives into configurations dense enough to become clouds, dense enough to form stars. The pattern is spatial: arm, medium, compression, cloud, filament, core, star, laid out across the galaxy in a repeating arrangement, playing out at slightly different moments at different locations, so that from outside, if you could see the whole galaxy at once in the kind of time-lapse that covers 1 billion years per second, it would look like the galaxy is breathing through its spiral arms, exhaling stars and inhaling the gas. Those stars will eventually return to the medium when they die. The medium is the breathing mechanism, not the lungs, the breath itself. Now pull back to the largest scale that makes sense in this context: the cosmic web. The interstellar medium inside a galaxy is connected by the galaxy's structure to the circumgalactic medium, the diffuse hot gas that surrounds the galaxy, extending out to several times the galaxy's visible radius. The circumgalactic medium is connected to the intergalactic medium, the even more diffuse gas that fills the spaces between galaxies, which is itself organized into filaments and voids by the large-scale structure of the universe. The arrangement of dark matter that pulled ordinary matter into the sheets and threads and knots that we call the cosmic web. The cold, dense core in the molecular cloud is one end of a chain that runs from the smallest scales of star formation all the way to the largest structures in the observable universe. Not metaphorically continuous, physically continuous. The gas in that dense core was, at some earlier point, part of the circumgalactic medium of the Milky Way. Before that, it may have been accreted from a cosmic filament, one of the large-scale threads of the cosmic web along which galaxies are strung like condensations on a wire. The core is collapsing into a star, and the core is made of matter that travelled here from outside the galaxy, along a filament that connects this galaxy to the large-scale structure of the universe across billions of light years of the oldest medium in existence. Zoom ends here. We're at the largest frame. Now the question at this scale: what fills the space between the filaments of the cosmic web? Voids, large regions, hundreds of millions of light years across, where the density of matter is significantly below average. Not empty. The matter is not gone. It is just thinned further, pushed to the walls and filaments by the gravitational dynamics of structure formation, leaving the interiors of voids genuinely sparse. The average density of matter in a void is perhaps 20 to 30% of the cosmic mean. There is still gas there. There is still the cosmic microwave background passing through. There are still dark matter halos, small and scattered. There is still, threading through even the voids, the magnetic field that permeates the universe at every scale. Weaken the voids, weak in a way that approaches the limits of our ability to detect it, but present. The void is not empty. The filament is not empty. The space between galaxies is not empty. The space between stars inside the galaxy is not empty. The space between atoms inside the medium is not. But that goes somewhere quantum mechanics lives, and this chapter is already wide enough. Back to the core. The collapse is underway. Over the next 100,000 years or so, the core will contract, heat, form a protostellar disk, accrete material, drive outflows that push back against the surrounding cloud, eventually ignite fusion, blow away its birth cloud with radiation and stellar winds, and settle into its life as a star. The medium made this, not as a passive container, not as a backdrop. The magnetic field in the medium threaded through the cloud and shaped the filaments, and the filaments fed the core and the core's angular momentum, inherited from the turbulent motions of the cloud, which inherited them from the turbulence of the medium, determined the rotation of the disk, which determined the geometry of the planetary system that will form around the star, which determined, somewhere down a chain of contingencies too long to follow, the arrangement of every object that will ever orbit that star. Everything downstream of the collapse carries the fingerprint of the medium that enabled it. The structure is filled. The filling is structural. Both things are true at every scale. It is magnetic fields, you have been told. And the telling happened early, probably in a classroom with a bar magnet and iron filings on a sheet of paper. The filings arranging themselves into those curved lines, north to south, a picture of something invisible made briefly visible by something small and iron and cooperative. Magnetic fields, you were told, look like that. Like a pattern around an object. Like a property of a specific thing. A magnet. A wire with current running through it. A planet with a liquid iron core. But that is the local version. That is the version that fits on a desk. The version that does not fit on a desk is this. The magnetic field of the Milky Way does not belong to any object. It is not the field of the sun, or of any star, or of the galaxy's central black hole, or of any identifiable source you could point to and say, this is where the field comes from. It runs through the interstellar medium the way a current runs through a river, which is a useful comparison only up to the point where it breaks down, and it breaks down almost immediately, because a river current is confined by banks and a bed, and the magnetic field of the interstellar medium is confined by nothing, threads through the spiral arms and between them, bends around the clouds and through them, extends out into the circumgalactic medium and beyond. Come back to the question from the other direction. How strong is it? About a few microgauss in the diffuse interstellar medium. This is a number that requires context to mean anything. The Earth's surface magnetic field is about half a Gauss. The field at the surface of a refrigerator magnet is somewhere around 100 Gauss. The interstellar field at a few microgauss is weaker than either of those by many orders of magnitude. It is, in the colloquial sense, extremely weak. And yet, orbit back to the thing that matters, not the strength at any one point, but what the field does, over the vast distances and long timescales of galactic structure. A charged particle moving through a magnetic field is deflected. This is the Lorentz force, and it does not require a strong field to operate. It requires only that the particle be charged and moving, and in the interstellar medium, both conditions are constantly met. Cosmic rays, high-energy charged particles, mostly protons and heavier atomic nuclei, accelerated to near light speed by supernova shock waves and other energetic processes, stream through the galaxy, and as they do, the interstellar magnetic field bends their paths. Not sharply. The field is too weak for sharp deflections over short distances. But over kiloparsecs of travel, the cumulative bending is significant. Cosmic rays do not travel in straight lines through the galaxy. They spiral, they drift, they diffuse through the medium along paths that are neither straight nor random but shaped, continuously and cumulatively, by the field they move through. The time it takes a cosmic ray proton to cross the Milky Way, if it travelled in a straight line, would be something like 100,000 years. The time it actually takes, spiralling and drifting through the magnetic field, is more like 10 million years. The field has lengthened the journey by a factor of roughly 100. That extra time is time the cosmic ray spends in the medium, interacting with it, ionizing it, depositing energy into it, heating it in a diffuse way that has real consequences for the chemistry and the structure of the gas. The field is not just guiding the cosmic rays, it is making them spend longer the neighbourhood. There is a structure to the field that took a long time to map and is still not mapped completely. The large-scale field follows the spiral arms of the galaxy, running roughly parallel to the arm axis, with a pitch angle that varies across the disk. But within this large-scale structure there is turbulence, small-scale fluctuations in field direction and strength that are tangled and complex, and within the dense regions of the medium, the field is draped around clouds, compressed ahead of shock waves, stretched along filaments, and occasionally locally amplified to strengths far above the mean. The field has geometry, not a simple geometry, not the clean dipole pattern of a bar magnet, but a real three-dimensional structure with coherent features at large scales and tangled complexity at small ones. Faraday rotation measurements, a technique that uses the rotation of polarized radio waves passing through a magnetized plasma to infer the field's direction and strength along the line of sight, have given astronomers a rough map of this structure. It is not complete. What the map shows is that the field is organized, not randomly tangled all the way down. There are large-scale patterns, reversals in field direction between spiral arms in some regions, coherent structures that span thousands of light years. Something maintains this organization against the turbulence that should, over time, tangle it into randomness. that something is the dynamo. Not a mechanical dynamo, a magnetohydrodynamic one, a process by which the differential rotation of the galaxy, combined with the helical turbulence of the interstellar medium, sustains and amplifies the large-scale magnetic field against the decay that turbulent diffusion would otherwise cause. The galaxy rotates differentially. The inner parts rotate faster than the outer parts, and this shearing motion stretches magnetic field lines that are embedded in the conducting gas of the medium, generating new field from old field, sustaining a large-scale pattern that would otherwise decay over timescales shorter than the age of the galaxy. This is the galactic dynamo. It is the reason the field is still there. It is the reason the field has structure rather than just noise. The medium conducts. It conducts because it is partially ionized. There are free electrons moving through it, and free electrons carry current, and current and magnetic field are locked together in the equations that govern and magnetize plasma, so that the field and the gas are not independent things but coupled. The gas moves the field, and the field moves the gas, and the two have been in this relationship for billions of years, each shaping the other, neither one primary. It is inside all of this, inside this coupling, this sustained dynamo, this billion-year negotiation between conducting gas and magnetic field, that everything in the galaxy moves. Every star, every cloud, every dust grain, every cosmic ray, every photon that crosses a long enough distance to be affected by the polarizing properties of the aligned dust grains that the field has organized. The field is not in the background. To be in the background, something must be separable from the foreground, must be removable in principle. Remove the galactic magnetic field, and the interstellar medium is a different medium, with different structure, different chemistry, different dynamics, different star formation rates, different cosmic ray confinement. The galaxy is a different galaxy. The field is not decorating the medium. The field is part of what the medium is, and the medium, and therefore the field, is the thing all of us, every star and cloud and world and anything that ever formed out of condensed interstellar gas, have been moving through since before the present version of the galaxy settled into its current shape. This field has been here longer than the sun. It has been writing itself into everything. It is already moving when this chapter opens. A grain of silicate dust, roughly 1/10 of a micron across, smaller than the wavelength of visible light, smaller than a bacterium, smaller than almost anything you have a word for, is drifting through the diffuse interstellar medium at a few kilometers per second relative to the surrounding gas. It has been drifting for a long time, long in a way that the word long can't quite reach. It was made in a star, not this star, not any star currently visible, a star that died before the sun existed, before the solar nebula had gathered itself, before there was a solar system to be inside of. An asymptotic giant branch star, swollen and slow and shedding its outer layers in a stellar wind, cooling that wind enough that atoms could condense, the way steam condenses on a cold surface, into solid grains. The grain formed there, in the cooling wind of a dying star, and then it left. The wind carried it out into the interstellar medium, and the medium received it the way the medium receives everything, without acknowledgement, without change in character, just, there is now a grain here that was not here before. The grain drifted. For millions of years, probably, it drifted through diffuse gas, absorbing ultraviolet photons and releasing them as infrared, building up a thin mantle of ice in colder regions, losing that mantle when it passed through warmer ones. It was hit at some point by a cosmic ray. The cosmic ray passed through it, ionizing atoms along its path inside the grain, leaving a track, a physical damage trail in the crystal structure, a record of the encounter. The grain carries this record now. It carries everything it has encountered, written into its structure in ways that require electron microscopes and mass spectrometers and careful laboratory analysis to read. Presolar grains, which is the name given to grains like this one that predate the solar system and survived its formation intact, have been found inside meteorites. The meteorites preserved them. The grains inside the meteorites still carry their records. Pick up the thread. The grain drifted into a molecular cloud. The temperature dropped. The grain's surface became a site, a meeting place for atoms and molecules that would not otherwise encounter each other in the gas phase, because the gas was too thin for gas phase reactions to proceed at any useful rate. But on the grain surface, molecules could stick, could meet, could react. This is called grain surface chemistry. The grain is a catalyst in the general sense, a surface that enables reactions. Water forms on grain surfaces in the cold. Hydrogen molecules form there. Complex organic molecules form there, not quickly, not in any process you could watch, but over the millions of years of the grain's transit through the cold medium, layer by layer, reaction by reaction, the surface accumulates chemistry that would not exist without it. The grain is not just a particle, it is a site, a place where things happen. Then the cloud collapsed. A nearby star formed, or a supernova shockwave passed through. Something disturbed the cold equilibrium of the cloud, and the grain was carried inward with the collapsing gas, toward the centre, toward the protostar. The icy mantle evaporated as temperatures rose. The molecules the grain had been carrying on its surface, the water, the carbon monoxide, the more complex things, were released into the gas phase around the forming star. They became part of the chemistry of the protostellar disk. Some of them ended up in comets. Some of those comets eventually impacted a young planet. The thread runs to here, and the narrator is still arriving, still finding the edges of what this means. The grain was made in a dead star. It drifted through the medium for longer than the sun has existed. It accumulated chemistry in the cold. It delivered that chemistry to a forming planetary system. The molecules it was carrying, which formed on its surface in the dark cold interior of a molecular cloud, are related. Not identical, not directly traceable in every case, but chemically related to the molecules that life on Earth requires. This is not speculation. The connection between interstellar chemistry, grain surface reactions, cometary delivery, and the organic inventory of the early Earth is an active and well-supported area of research. Complex carbon molecules are found in meteorites. The chemistry is real, and the chain is real, and the grain is a link in it. The grain that knows something, it turns out, was carrying it here the whole time, in the slow, patient way that things travelling at a few kilometres per second across thousands of light years of interstellar space carry anything, without hurry, without intention, but with a certainty that comes from having nowhere else to go and all the time in the universe to get there, which is perhaps the only kind of certainty that actually arrives. From a certain remove, the interstellar medium looks like a problem of statistics. Not a physical problem, not initially. Not a question about forces or fields or chemistry, but a question about counting. About how many things are in how much space, and what the distribution of those things implies for the probability of any one thing encountering any other thing. It is a problem that can be set up in a few lines of mathematics and solved, in principle, without reference to any specific star or cloud or region of the galaxy. The math doesn't know where it is, it just knows the numbers, and the numbers are strange. The mean free path. This is the concept the chapter deposits first, quietly, before anything else. It is the average distance a particle travels between collisions in a gas at room temperature and pressure, the air in this room, the air you're breathing. The mean free path of a nitrogen molecule is roughly 68 nanometers, 68 billionths of a meter. The molecule travels that distance statistically before it hits something else. Then it changes direction. Then it travels another 68 nanometers. The collisions happened billions of times per second per molecule. In the diffuse interstellar medium, in the warm neutral phase, which is one of the several distinct phases of the medium, and the one that occupies perhaps 30 to 40% of the volume of the galactic disk. The mean free path of a hydrogen atom is on the order of 100 astronomical units. 1 AU is the distance from the Earth to the Sun. 100 AU is roughly the distance to the inner edge of the Oort cloud. This is not a dense region. A hydrogen atom in the warm neutral medium travels on average the distance across our entire planetary system before it hits another hydrogen atom. Layer 2 deposits now, without comment. The number density of the warm neutral medium is approximately 1 atom per cubic centimetre. 1. The air in this room contains roughly 27 million billion molecules per cubic centimetre. The diffuse interstellar medium, in this phase, contains 1 atom per cubic centimetre. A cubic centimetre of air holds the equivalent of a small city's worth of molecules in constant collision. A cubic centimetre of the warm neutral medium holds 1 atom drifting. And yet the physics does not simplify. This is the thing that surprises people when they encounter it for the first time. You might expect that a medium this thin would behave simply, that with so few particles per unit volume, the interactions would be rare enough to be ignorable, the dynamics clean enough to be described by a few basic equations, the chemistry essentially non-existent. Empty space behaving like empty space. It doesn't. The warm neutral medium has a temperature, roughly 6,000 to 10,000 Kelvin, which is hot, which is as hot as the surface of the Sun and hotter than most stars' photospheres, which is a number that requires a pause. The diffuse interstellar gas in this phase is as hot as the surface of the Sun and contains 1 atom per cubic centimetre, and both of those facts are simultaneously true. This is where the two temperatures from Chapter 3 echo without being repeated. The number is real, the kinetic energy per particle is real, the heat is real, but because there is almost nothing there, almost nothing transfers that heat to anything. A thermometer placed in the warm neutral medium would not read 10,000 Kelvin. It would read whatever its radiation equilibrium temperature was with its surroundings. The temperature of the medium is a property of the particle's motion, not of anything you could feel. The heat is there. It just has nowhere to go and nothing to touch. The distance between collisions in the hot ionized medium, the third phase, the gas that fills the bubbles blown by supernovae and stellar winds, which occupies perhaps 50% of the volume of the galactic disk, despite being even thinner than the warm neutral medium, is longer still. The hot ionized medium has a temperature of roughly 1,000,000 Kelvin, 1 million, and a particle density of perhaps a few thousandths of a particle per cubic centimetre. At those densities, the mean free path is not 100 astronomical units. It is measured in light years. A proton in the hot ionized medium travels for light years between collisions. It is moving at a speed consistent with 1,000,000 Kelvin. It is almost not hitting anything. It is crossing stellar distances between encounters, and it is doing this continuously, as part of the normal behavior of the gas that fills the bubbles of the interstellar medium between the denser filaments and clouds. Layer 3. The phases of the medium coexist: cold molecular gas, cold neutral gas, warm neutral gas, warm ionized gas, hot ionized gas. These are not regions that exist in isolation. They are interleaved, adjacent, often in pressure equilibrium with each other, which means that the hot thin gas and the cold dense gas can sit next to each other without one immediately consuming the other, because their pressures, despite their enormous differences in temperature and density, roughly balance. Hot and thin, cold and dense, pressure equal. This balance, called the two-phase medium in the version formalized by Field, Goldsmith and Habing in 1969 and extended to more phases since, is not a coincidence. It arises from the heating and cooling processes that operate in the medium, the ultraviolet radiation from hot stars that heats the diffuse gas, the line emission from atoms and molecules that cools denser regions, the cosmic rays that provide a diffuse heating floor throughout. The phases are the stable solutions to the thermal equilibrium equations. The gas self-organizes into these phases the way water self-organizes into ice and liquid at 0 degrees, not because someone arranged it, but because the physics has preferred states, and the gas finds them. The mean free path, the phases, the temperatures, these are deposited now, one on top of the other, without being resolved into a single picture. They make a picture, but the picture is not the kind that snaps into focus. It is the kind that takes time, that you look at and then look away from and then look back at, and each time you look you see a bit more of the arrangement. The interstellar medium is thin almost beyond imagining. It is hot in places that cannot burn anything. It is organized into phases that coexist at wildly different temperatures in rough pressure equilibrium. It is structured at every scale, and in it, atoms travel for light years between collisions, drifting through a space that is almost empty except for the fields and the radiation, and the history that fill it as thoroughly as the atoms that are nominally the medium do. The atom crossing the warm neutral medium between one encounter and the next is not alone. It is bathed in radiation. It is threaded by the magnetic field. It is being nudged by the pressure of cosmic rays. It just hasn't hit anything in 100 astronomical units. An ultraviolet photon arrives. It has been travelling from a hot young star, an O-type or B-type star, the kind that burns blue-white and lives fast and dies in supernova, the kind whose radiation budget includes enormous amounts of ultraviolet light, and it has been travelling since it left the stellar photosphere, crossing a distance that took it through the diffuse interstellar medium, and now it has arrived at the edge of a neutral hydrogen cloud, and it has enough energy to do something that lower energy photons cannot do. It ionizes, It collides with a hydrogen atom, transfers more than 13.6 electron volts of energy, the ionization threshold of hydrogen, and the electron that was bound to the proton is no longer bound. It is free. Two things where one was: the region around a hot young star where this is happening constantly, where the radiation is energetic enough and intense enough to keep the surrounding hydrogen ionized, is called an HII region. The notation is straightforward. HI means ionized hydrogen, one proton with its electron removed. The sound of it, though, the sound is not in the notation but in what's happening in the gas. A free electron moving through an ionized plasma, decelerated by the electric fields of the protons it passes near, emits radiation. This is called free emission, or Bremsstrahlung, a German word meaning breaking radiation, from the way the electron is slowed, briefly, by each encounter. It emits across a broad range of radio frequencies. A large HI region broadcasts in radio. It is one of the sources that makes the galaxy glow at radio wavelengths. The medium is noisy in the physics sense. It is emitting continuously in the frequencies that radio telescopes hear, because of the constant cascade of events that the ionization initiates. The electron that was freed, it does not stay free indefinitely. In an ionized medium, free electrons and protons recombine. The electron falls back toward a proton, is captured into an excited energy level, and cascades down through the level structure, emitting photons at specific frequencies as it goes. The most famous of these is the hydrogen alpha line, a photon emitted when an electron drops from the third energy level to the second at a wavelength of 656 nanometers. Red, visible to the eye. HII regions glow red. The Orion Nebula glows red. The Eagle Nebula glows red. The red in those images is not false color, not an artistic choice, not infrared remapped. It is the actual color of hydrogen recombining, of electrons finding their way back to the protons they were stripped from. The ionization and the recombination are in balance, roughly. The star keeps ionizing, the medium keeps recombining. The boundary of the HII region, the Strömgren sphere, named for the astronomer who first worked out its physics, is the radius at which the ionizing photon flux is exactly sufficient to maintain the ionization against the recombination rate. Outside that boundary, neutral. Inside, ionized. The boundary is not a wall, it is a balance, held by the continuous spending of the star's ultraviolet budget against the continuous recombination of the medium. The charge that ionization creates does not stay local. The narrator will say this, and then admit some uncertainty about how clearly it can be followed. The effects of ionization propagate outward from the HII region in ways that are not simply about the direct radiation. The ionized gas is hot, 10,000 Kelvin, and it has pressure, and pressure differences create flows, and the hot ionized gas expands into the surrounding neutral medium, compressing it, sweeping it up, creating dense shells at the boundary of the expanding HII region. Those shells are dense enough in some cases to trigger star formation. The compression of the shell drives the neutral gas into a configuration where gravity can take over. The expanding bubble of ionized gas created by the radiation of one generation of massive stars triggers the collapse of the neutral gas at its edge, which forms the next generation of massive stars which ionize their surroundings, which creates new bubbles. This is called triggered star formation.
The medium does not just respond to the stars that form inside it. It transmits the influence of those stars outward, converting that influence into new structure, new density concentrations, new nodes where the next generation of stars will eventually form. The charge
Distributed itself, moved through the medium, did work. There is a particular quality to all of this that resists being described cleanly. The medium is not passive. That has been established repeatedly throughout this audio. But the ionization process has a specific character that the other processes don't quite share. It is violent in a way that is easy to underestimate. A supernova, yes, supernovae are obviously violent, but a single O star sitting in its own ionized bubble is continuously converting its surroundings, pushing them, rearranging them at a rate and with an effect that, summed over the hundreds of thousands of years the star lives, amounts to a substantial reshaping of the local medium. And the medium, and this is where the uncertainty lives, the medium absorbs this. It takes the ionization, the heating, the compression, the triggering. It responds, it reorganizes, it finds a new configuration. Whether the net effect of massive stars on the star formation, efficiency of the medium is positive or negative, whether they trigger more star formation than they suppress, whether the compression they cause forms more stars than the heating they produce prevents from forming, is a question that current research has not fully settled. The medium receives the charge. What it does with it exactly is still being worked out. Something is about to be received. The dish is pointed at a region of sky that optical surveys have confirmed contains nothing of note. No bright stars in the foreground, no catalogued nebula, no galaxy cluster in the background that would account for what the instrument is about to record. The coordinates were chosen because a model predicted that this region of the interstellar medium should be emitting, and the dish is here to confirm or deny the prediction, and the receiver is cold, and the amplifiers are running, and the strip chart is moving at its steady pace, and in approximately the next few seconds, at the frequency the model predicted, a signal is going to arrive that crossed hundreds of light years to get here. We are standing beside this, not ahead of it. Radio astronomy and the interstellar medium grew up together, which is the kind of sentence that becomes more interesting the longer you orbit it. The discovery of the 21 centimeter line, the hyperfine transition of neutral hydrogen, mentioned briefly in the first chapter and now given more room to breathe, was predicted in 1944 by the Dutch astronomer Hendrik van der Hulst, working from theory during the German occupation of the Netherlands, in a period when the kind of work that requires large instruments and institutional support was not easily available. And so the work that could be done was the work that required only a mind and a notebook. Van der Hulst calculated that the transition should occur, calculated its frequency, and calculated that the interstellar medium should contain enough neutral hydrogen emitting at this frequency that a radio telescope should be able to detect it. He published the prediction. He then waited. The detection came in 1951, independently, by three groups: Harold Ewan and Edward Purcell at Harvard, C. Alex Muller and Jan Oort in the Netherlands, and Frank Kerr and Joe Pawsey in Australia. Three groups, three instruments, three confirmations, arriving within a few months of each other, as scientific confirmations sometimes do when the instrument technology and the theoretical prediction mature at roughly the same moment. The 21 centimeter line became, and remains one of the most important observational tools in radio astronomy. Orbit the 21 centimeter line, come at it from a different angle. Why does the hyperfine transition emit at all? The hydrogen atom has a proton and an electron. Both have a quantum property called spin. Not literal spinning, but an intrinsic angular momentum that behaves in some ways like a spinning top, and in other ways like nothing familiar at all. The proton and electron can have their spins aligned, pointing the same direction, or anti-aligned. The aligned state has slightly higher energy. When the electron flips from aligned to anti-aligned, the atom releases the energy difference as a photon. The energy difference is tiny, equivalent to about 5.9 millionths of an electron volt, compared to the 13.6 electron volts required to ionize hydrogen, and the probability of any individual atom making this transition is low, roughly once every 11 million years per atom. 11 million years. This is the duration embedded in the signal. Each photon at 21 centimeters represents an event that, for any individual atom, happens once every 11 million years. And yet the signal is detectable, is bright enough to map the entire galaxy with, because the galaxy contains an enormous amount of neutral hydrogen, on the order of several billion solar masses of it, and even at a probability of once per 11 million years per atom, the number of atoms is large enough that the signal is continuous and strong. The medium is patient, and there is so much of it that patience produces a steady output. Orbit further, come at the signal from the direction of what it tells us. The 21 centimeter line has a precise rest frequency. When it's received at a slightly different frequency, Doppler shifted by the motion of the emitting hydrogen relative to the observer, the shift tells you the velocity of that hydrogen along the line of sight. Map the line across the sky, measure the velocity at every position, and you have a three-dimensional map of the neutral hydrogen distribution in the galaxy, because the Doppler shift translates directly to distance in a galaxy where the gas follows a known rotation curve. This is how we mapped the spiral structure of the Milky Way. Not with optical telescopes. The dust in the medium blocks optical light along most lines of sight through the galactic disk. With the 21 centimeter line, which passes through dust without being absorbed, which carries its own distance information in the form of the Doppler shift, which is emitted by the dominant component of the interstellar medium everywhere in the galaxy. The medium mapped itself. The neutral hydrogen emitted the signal carried the velocity encoded the position. We pointed instruments at the sky, and the medium told us where it was and where it was going. Orbit once more, from the direction of what the medium emits beyond 21 centimeters. The interstellar medium is a complex emitter. Carbon monoxide, the second most abundant molecule in the medium after hydrogen, emits at millimeter wavelengths and has been used to trace the distribution of molecular gas, the cold dense phase, throughout the galaxy, because molecular hydrogen itself is almost impossible to observe directly, and carbon monoxide is a reliable proxy for it. The hydroxyl radical emits at 18 centimeters, formaldehyde at 6 centimeters, ammonia, water, methanol, all observable, all distributed through the medium, all broadcasting their presence to instruments pointed in the right direction, at the right frequency. The medium is not emitting one signal. It is emitting a spectrum of signals, each one from a different component, a different molecule, a different physical process, each one carrying information about the region it came from, its temperature, its density, its velocity, its chemical composition, the intensity of the radiation field it is embedded in. The radio sky is full of the medium talking about itself. The dish is still pointed at the region of apparently empty sky. The signal arrived. It was at the predicted frequency. It was the 21 centimetre line. The model was confirmed. The neutral hydrogen was there, in the dark, in the gap that the optical surveys said was empty, emitting steadily on its 11 million year schedule, one atom at a time, adding its photon to the photons of the billions of other atoms emitting the same transition in the same region, producing a signal that crossed hundreds of light years and arrived in a dish on the surface of a planet and was received. The dark talked. Something has been building through all of this, quietly, without announcing itself. It is finished now, or it is nearly finished. The thread that was picked up in the first chapter, that the dark gaps between stars are not gaps, that the interval has texture and behaviour and deep time, has been followed through chemistry and magnetism and ionization and the long empty distances between collisions, and it has arrived here at the last chapter, not with a flourish, but with the particular stillness of a thing that has been completely said. The thread is down. This chapter is only the space where it settles. The word that was used, terrifying, deserves a moment. Someone chose it, not randomly. With the intention of producing a specific response in a person who has just looked up at the night sky and felt the comfortable weight of all that familiar darkness, the darkness that is background, that is stage, that is the thing the eye passes over on its way to the stars. The word was chosen to interrupt that comfort, to make the dark feel different, to shift the ground slightly under the picture the listener has been carrying, and the science supports the word up to a point. The interstellar medium is a structure of genuine consequence. The magnetic fields threading through it shape the path of cosmic rays that pass through the solar system. The heliosphere, the bubble of solar wind that surrounds the solar system and partially shields it from the interstellar medium, is in active contact with the surrounding medium at its boundary, the heliopause. The pressure of the interstellar medium shapes the heliosphere. The density and temperature and magnetic field of the local medium affect the geometry of the boundary that separates the solar wind from the interstellar wind. We are inside the heliosphere. The medium is pressing against it. This is what the word terrifying was reaching for. Not that the medium will do something sudden, not that there is a threat in the conventional sense, but that the picture of the solar system as a discrete bounded object sitting in empty space is not quite right, and the correct picture, a bubble in a medium shaped by the medium, in dynamic equilibrium with the medium, moving through the medium at roughly 20 kilometers per second relative to the local standard of rest, changes the feel of where we are. We are not sitting in emptiness. We are moving through something. The something has properties. The something pushes back. The sun, in its orbit around the galactic center, has passed through regions of the interstellar medium with different densities and temperatures over its 4.5 billion year history. During periods when the solar system moved through a denser region of the medium, a molecular cloud, a compressed shell at the edge of a supernova remnant, the heliosphere was compressed. The boundary moved inward. The shielding against galactic cosmic rays was reduced. The cosmic ray flux at Earth increased. There is ongoing research, contested and unresolved, into whether these passages correlate with anything in the geological record, with ice ages, with extinction events, with periods of elevated mutation rates. The connection is plausible in mechanism and disputed in specifics. The narrator will not overstate it. But it is there, in the literature, not as fringe speculation, but as a mainstream question being worked on by careful people. The medium may have had a say in the history of life, not because it is hostile, not because it is indifferent, in the way that the word indifferent sometimes gets applied to the universe by people making a point about human significance. The medium is not indifferent. Indifferent implies a withholding of attention, and the medium has no attention to withhold. It simply is. It simply does what its physics requires it to do, which is to have density and temperature and pressure and chemistry and magnetic field, and to exert those properties on everything that moves through it, including the heliosphere, including the boundary that separates us from it. The terrifying part, if there is one, is the ordinary, not the discovery of something monstrous in the dark, not a threat, not a secret the universe was keeping, just the quiet realization that the dark was never background, was never the stage, was never the empty space between the things that matter. It was always one of the things that mattered. It was always exerting influence,